Me. Channel 1? Ah, channel 1. All right. All right, so now I apologize if you didn't like the way I marked something. You know what? I'll give you a little bit of history. I used to work full-time for Edmonton Public and taught for them for many, many years. And about 4 or 5 years ago now, I retired. And so I still do occasional teaching, especially for people that I know. And I do know your teacher. And in fact, Mrs. Johnson used to be my student a long time ago. And I want to tell you something about her. She was a very good student. All right. I actually taught her in Physics 20. That's the course I ended up teaching her in. And she was a very pleasant, hardworking student. So whenever she assigns homework, I want you to know she practices what she preaches. Right? So she certainly was very good at homework completion, just like you guys are. So it's all good. All right. So the other thing I've tried to do is I've tried to keep aware of what's ahead of my students. So I have communicated with various professors at the U of A and Grant MacEwan about the calculus courses there, because I always want to know where are my students going. What's going to be? It's our little secret. Oh. Okay. All right. Now, I always like to be aware of what my students are going to be facing in the future. Some of you may have heard this rumor that first-year calculus is the most commonly failed course in university. That rumor is actually true. I'm not trying to scare anybody here, but you guys are off to a really good start. Those students that have a really good mark in Math 31 are far less likely to fail calculus. But the university professors' standards are quite exacting, all right? So I noticed that on your assignments, sometimes your teacher was saying solve algebraically, and it was underlined. And there's certain standards that they have for you, all right? So I'm going to try to lay down some of those standards for you. I don't think it's that onerous. I think it'll be something that'll come naturally to you in a while. Most of your communication was really good on the exam. The only part where we seem to struggle a little bit as a group is dealing with the definition of continuity and what was continuous, what was not, and how to demonstrate when something was continuous and when it wasn't. And some of you just said, well, the point doesn't equal the line, which I know what you mean, but it's not an official way to demonstrate continuity. And I don't say that to be mean. I just say that to say this is what's ahead of you, okay? And I still actually am tutoring calculus students from the U of A, and I enjoy that. And sometimes I provide it for free because I just enjoy that course so much. And I think you're really going to like it as well. Okay, let's start with notations. One word of warning about this particular lesson. It does have at least a PG rating. No, not for language, but it is going to be rather violent action. Not on my part, okay, but we're going to have to go quite quickly. When I got the outline from your teacher, it said there was an asterisk and said long lesson. And then I realized it's for a short day. Oh my goodness, long lesson in a short day. So can you fasten your seatbelt and just hang on? Here we go. All right. All right, so first of all, what are the symbols for a derivative? Okay? You already know, and probably your teacher talked to you about this, that a derivative, of course, is a way of measuring the slope for a curve at any point. A straight line, anybody can find slope of a straight line. y2 minus y1 over x2 minus x1. It's simple. But what if the line is curving? What if we want the point at a particular place in that curve? We want its slope right then. Okay? Let's take a look at some of the symbols for derivative. dy over dx is the most famous symbol. And it's probably used quite often today. If you're in a rush, you can just write what's called y prime. That symbol is called a prime. It's like a hyphen, okay? So if you don't have time to write out this whole symbol, you can just write y prime, all right? A couple of more symbols, f prime of x, all right? That also means the derivative. And then d f of x over dx. All right, so that also is the derivative. Now, in addition to this, there's an old-fashioned symbol, which I'm not going to even put in the box. If you do happen to check some resources in some older textbooks, that symbol was used for the derivative in some of the older textbooks. I hardly ever see it being used today. So I guess you could say there are fashions in math as well. Things that fade in and fade out of popularity. And so this one seems to be fading out right now, capital D of x. All right, so we're going to talk about the two interpretations of the derivative right now. There are two interpretations, number one and number two. What are they? Well, of course, tangent slope. When you found the slope of a tangent in our previous unit, you were finding the slope at an instantaneous point of the curve. All right? So that's always good to know. Of course, if our curve is a straight line, that slope will not change. So if we took the derivative at any point on this line, we should expect it to be exactly 1/3. So whatever formula we come up with for the derivative better show us the same value as traditional methods for linear graphs. All right, so for number two, you can also think about a derivative as an instantaneous rate of change, right? So a derivative shows how quickly y changes for a given change in x. Another thing to keep in mind is that the higher the derivative is in value, the faster the y-coordinate is changing with respect to x. If you have a positive slope, that means, of course, that the y value is increasing. And if you have a negative slope, we have a y value that's decreasing. This means that the sign of the derivative is also important to us. If the derivative is positive, that means your slope is positive. That means you have an increasing part of the function. All right, first page, not too bad. You survived your first page. Congratulations. All right, here we go. Okay, what about your two old friends? The one you like, f prime of a, is going to be the limit as x approaches a of f of x minus f of a all over x minus a. So we're now in position to put something different than we did before. Before we had mt equal to that, didn't we? Now we can put f prime of a. Okay, this is our derivative at a, all right? So this was fine for last chapter. Now we're moving on to this, all right? And your least favorite formula, the h formula. Still a very valuable formula. All right, so you, in a way, voted with your exam. And we had 22 votes for number 1 and 1 vote for number 2. So if we took a survey of university calculus professors, I wonder how they'd vote. I would suspect the majority of them would go with number 2. That's what I've seen. That's what I have seen in most textbooks. Okay. All right. But in this unit, we will want to find the slope of tangent lines for all points of x. Not just point A, but in general for all points of x. So keep in mind that we started with a secant slope, right? Connecting point P and point Q with a straight line, and then allowing Q to float down the curve towards P. So the slope, delta y over delta x, right, could have been found by taking f of x plus h and subtracting f of x. And on the bottom, so that's y2 minus y1. On the bottom, x plus h minus x. Turns out that the bottom can be simplified. So on the bottom, we just have h, right? Now, of course, our slope, MPQ, will eventually become MT, won't it? As we allow Q to slide down the curve, then our x-coordinate is approaching our A, and our MPQ is approaching MT. Thus, we can say that this limit is equal to this limit. Now, since it's not rocket science here, all we did was we took our original formula, which had A's in it, and the A has been replaced now with X. So you could say that finding the derivative is a generalization of finding the tangent at A. So in the past, you were interested only in coordinate A, whatever A was. It was a number. Now we're going to do it more generally. We're going to do it for all x. All right, so the formula that we come up with won't just be true for x equals 2 or x equals -7. It'll be true for all x's, and that's the powerful part of the derivative. Okay, so I'm trying to build like a little bit of foreshadowing like they do in English class here. Okay, so there's the new formula. Okay, it's right here. F of x plus h minus f of x over h. The formula calculates the slope of the tangent for any value of x. And I know you're all really anxious to actually do a question using this formula. So let's do that. All right. In the interest of time, I've decided to assign example 2 for homework. All right, but we will do example 1 and 3 together. It's a compromise, okay? But for me to get through this lesson on a short day, we're going to do this for homework. We're going to do 1 and 3 for right now. Okay, so let's do this first one. We begin by writing our derivative symbol, f prime of x. I could also write dy over dx. But for this application, the definition, we usually use this particular symbol. All right, so let's write it out in general. The limit as h approaches 0 of what? F of x plus h minus f of, sorry. All right, so there's the formula in all its glory. So all we have to do is substitute in now. There you go. That wasn't so bad. So for f of x plus h, I've taken out the x from 3x squared. And what did I put in place of it? X plus h. Are you on board? And then over here, what have I done? X squared. So if we were doing tangents, we'd had a number in the brackets here. But now that we're not doing tangents, it's all variables. It's all variables in our numerator here. So it might be a little bit more difficult to simplify because we have no numbers in here, just variables. All right, so let's take a look. Whoops, didn't mean that bracket right there. Once again, there really isn't enough space on here, so I'm going to continue this on the whiteboard. Yeah, I lose the recording. I think since we're not doing this in class, we'll just sort of pretend it's not here and keep going. All right. So then we have all right, so just distribute through the 3 through the brackets. How many know what my next step would be? Yes, the 3x squared, right? So even though we're working with variables, the procedures are much the same as what you did last unit. Factor out the h just like you did before, right? You could also factor out a 3, but you don't necessarily have to. As you can see now, h, which is the factor that was giving you 0 over 0, is now eliminated. The h's can now cancel out. The resulting expression is a determinate limit, meaning you can substitute in. What do I get if I substitute 0 for h? 6x. 6x plus 0, or 6x. That's my derivative here. The derivative of 3x squared is 6x. So if you were to graph the curve 3x squared, it's a quadratic that's fairly steep because of the 3 in front. And you wanted its slope at any point, all you need now is the x-coordinate. For example, if the x-coordinate is 1, the slope at that point will be 6. If your x-coordinate is 2, it'll be 12. Very simple. So this is called the derivative. This is now a formula to find the slope at any point of 3x squared. All right? What's that? Okay, so to differentiate means to find the derivative. Okay, so that's all it means. Differentiate in example 2, right? Now I'm going to give you a head up with this example 2 thing. We really have to move on here, but for example 2, That one, f of x equals x to the 6. The first step would look like this. That's what the first step of 2a would look like. Now this one will require some very careful work on the simplification. Do you know how to raise a bracket to the 6th power? Now, you guys are taking Math 30-1 at the same time, right? You actually need something from there for a shortcut called Pascal's triangle. So I'm not sure if you've studied it yet, probably not. So this is sort of a nasty question for us right now. So maybe don't do that one. Do B and C. And don't try D unless you want a splitting headache. No, I mean, try D if you want a real challenge. But a more standard question would be example 3. Okay, moving on to example 3. And don't let the assignment thing fool you right here that we're not done the lesson there. All right. Okay. I want you to take a look at my first step for example 3. By the way, all the questions in example 2 are a little bit overkill in my opinion. They probably wouldn't be found in most Math 31 classes, but your teacher likes to give you some challenge. So example 2 is definitely challenge questions, but this is more of a standard question, just like example 1 was more of a standard question. This one could definitely be asked on an exam. All I want you to do right now is see if I did the first step correct. Did I substitute correctly? In the first expression, do you see an x plus h where x used to be? And in the second expression, is it identical to the given one? Yes. So this is a correct first step. Now, how good are you at fractions? How good are you at fractions? Because that's really what this comes down to, doesn't it? We're going to have to, now, if you want to simplify this numerator first, you could. So let's just get that out of the way. Here I have 3 minus 2x minus 2h. And then, whoops, I didn't mean a long fraction bar there. All right, class. We will need a common denominator for these two fractions, won't we? The common denominator will simply be the product of these two. And by the way, don't multiply those out. Just leave them as 2 brackets. So the next step will look like this. 4 plus x plus h, 4 plus x on top, 3 minus 2x minus 2h times 4 plus x, and then minus 3 minus 2x times 4 plus x plus h. All right, so our numerator is looking a little bit complicated. So what I did was I made these two my common denominator. This one already has this factor, so I gave that numerator the other factor. Similarly, I gave that numerator this factor. It's like I cross-multiplied, right? Okay, where is the work going to come now? The work comes in multiplying this together and this together. Now, I have a way of predicting how successful you'll be with this. And the question is, how tidy is your room at home? In other words, are you a careful person? Because that's what this is all about. This is about being careful. Keep in mind, class, that this is actually h over 1, isn't it? So when you divide it, you take the reciprocal. All right, so what will this look like? In the denominator, and we need a big space here, h will join these two in our denominator. Once we take the reciprocal and multiply, there'll be another h down there. Okay, I'm now going to attempt to multiply this binomial by this trinomial. So we'll do that. It'll give us 12 plus 3x minus 8x minus 2x squared minus 8h. Let's just see, 12. Yeah, 12, 3x minus 8h minus, 12 plus 3x minus 8x minus 2x squared minus 8h. The last one is negative 2xh. So I've got all 6 of my products there. You might want to put a bracket around that because you will be subtracting the other ones from it in here, if I can fit them in there. All right, so this one will be 3 times 4, so 12. 3x, 3 times h, 3h, minus 8x. Will I make it? Minus 2x squared. And the last one, minus 2xh. I have to put him up like that. All right, yes. Yes? Yeah, so what this is you're dividing by h over 1. So up here you'd be multiplying by 1 over h. The reciprocal, right? Yeah. So if you take this off here, then it's 1 over h up there. Right. All right, class, your eyes are probably better than mine. What terms will cancel out in your numerator? The 12, the 3x, the 8x, the 2x squared, the 2xh. So there's identical terms in both brackets for 5 of the 6 terms. All that's left is negative 8x, negative 8h, minus 3h. So that's negative 11h. I I am not going to multiply through the brackets in the denominator. It would be a waste of time. So now the h's cancel. Once those h's cancel out, your limit will become determinate every time. That means you can find it by substitution now. So go ahead and substitute h as 0. What will it look like if h is at 0? Negative 11 would still be the same on top. And on the bottom, you'd have 4 plus x squared. And that, ladies and gentlemen, is your derivative. Do you see how careful I had to be, though? And that's the... Now, you guys are not going to like me tomorrow, because tomorrow... Oh, h is going to 0, right? But if it cancels out before you do the limit, that's fine. Yeah, yeah. Now, tomorrow we're going to learn a shortcut way of finding derivatives. So we don't have to do this formula every time. Okay. Okay, what's your domain for the original? All right, for the original function, what's your domain? For the original function, the domain is x not equal to negative 4. What's the domain for the derivative? It's exactly the same. That usually happens, but not always. Sometimes the derivative is a little bit more fussy than the original function. Yeah. Yes? All right, but remember, it's not at 0 yet. It's just close to 0. All right? All right. Let's go to, whoops, wrong one. Oh, it's the right one. This is part 2. Okay. I can't believe I have to do this on a short day, like there's 10 minutes left. It's not going to happen. But then we'll be behind. You know what? I'm just going to give you a very brief, this part actually goes pretty quick. All right? Okay, pretty quick. The first thing I want to say is that if your original function has 0 slope, the derivative will have an x-intercept. That means the derivative is 0. So it'll be an x-intercept on the graph of the derivative. If you have positive slope, of course you'll have a positive y-coordinate for the derivative. And if you have negative slope, you'll have a negative y-coordinate. There should be 2 more rows here. I'm going to just put them in. Asymptote. If you have an asymptote, of course, then the derivative will be undefined there. You can't measure the slope of something very steep like that. And if you have what's called a cusp, also called a corner or a kink, there's different words, then you'll have a discontinuity in the derivative. Okay. In the next 5 minutes, we will demonstrate how to draw derivatives, draw the graph of the derivative if you have the original graph. The first thing I want to look for is where I have 0 slope. I have 0 slope here, and here, and here. So I have 0 slope at -3. Put an x-intercept at -3. I have 0 slope at -1. Put an x-intercept at -1. And then again at +1. So what will our derivative graph look like? We're starting with negative slope, then positive slope, then negative, then positive. So it's got to be something like this. Our derivative has to start out negative, then be positive for a while, then go negative for a while, and then go positive for a while. This is actually a degree 4 graph, quartic. The derivative is actually a degree 3 graph. We lose a degree. So I'm wondering, if you started with degree 2, what degree would the derivative have? 1. And watch this. Where do you have 0 slope? Right at 0. So we have an x-intercept right here. You have negative slope here and positive slope here. I'm thinking this one looks like that. So negative derivative where you have negative slope. Positive derivative where you have positive slope. See, I told you this part will go a little faster. Now, just a couple more, just 2 more here. Then we'll be done for today. We'll be done for today. Let's finish with 3 and 4 here. Okay, with question 3, we have a domain restriction. We can see that x is not equal to -2. So we have an asymptote there. So look what you have before that. You have negative slope, that's getting more negative. So we're going to be undefined at -2 in our derivative. So draw a dotted line right there. And we have negative slope for this entire region of the curve. So the derivative will be similar to the actual function. You'll have a negative portion of your derivative there. And it's getting more and more negative as we get closer to infinite negative slope there. The right-hand side of the curve, the slope is positive at all points. That means our derivative, the slope is negative at all points. Our derivative will be negative at all points here as well, but less negative here than here. So this derivative actually would be like this. Its curve has to show negative y coordinates here because you have negative slope up here. And in our last example, we have a cusp, also called a corner, right? You can call that a cusp or a corner. And the derivative is never defined at a corner. Our slope here is negative, and our slope here is positive, and it's not changing. That means we have a constant slope on the left, a constant negative slope, and then all of a sudden, a constant positive slope. This one, the slope is -1. So let's draw a horizontal line here at -1. This one, the slope is +1, so let's draw a horizontal line here at +1. And guess what? An open circle on both of them. Isn't that weird? So there is no derivative at the corner. If you had to draw a tangent line on that corner, where would it go? All kinds of ways. You could draw a line like that, like that, like that. They all touch the curve at one point. So whenever you cannot locate a specific tangent, that means there's no derivative at that point. Open circle, open circle. our class, so we got about 1.5 lessons done. All right? Yeah. Well,